All right, in this screencast, we're going to talk about acid rain, something I think most of us have heard about, but I think a lot of people don't really understand what exactly it entails and how it's caused. So let's see if we can fix that. Before we can talk about acid rain, we need to just talk about acids and what they are and what they do. Okay, so I'm sure you remember from chemistry pH. So in pH, the P stands for the negative log of the concentration in moles per liter of, and then H is the hydrogen ions. So basically, it's just a way of keeping track of the molar concentration of hydrogen ions in a water solution. Now, so if we think about just pure water, just absolutely nothing but the compound H2O. Well, it turns out in H2O, even though it's made of molecules of H2O, these molecules have a tendency to spontaneously on their own disassociate into H ions and OH ions. So if I take one of these and break it apart into two ions, I will get one H ion and one OH ion. So they will occur in equal concentration, and the water will be what we call neutral. It will not be acidic or basic. Now, in 1 liter of water, what we'll find is what is the concentration of these ions? And it turns out it's a very low concentration. It's 10 to the negative seventh moles per liter. So it's not very concentrated at all. Very, very few. So, I mean, that's a small number. I guess a very tiny concentration, but it's present in pure water. So, so if I take the negative log of this number, basically the log would be -7, and then the negative log would just be 7. So it's just a way of keeping track of the concentration. So if I take the negative log of 10 to the negative seventh, which is the molar concentration of hydrogen in pure water, I get the number 7. So what we do, just for a shorthand way of describing it, we just say the pH of pure water is 7. Now, an acid is, and there's different ways of defining acids, you probably remember from chemistry, but we'll just use this one here. An acid is a substance that, when added to water, causes an increase in the concentration of hydrogen ions. So, for example, let's just take hydrogen chloride, HCl, hydrochloric acid. If I add HCl to water, the HCl dissociates, forming H ions and Cl ions. Now, Cl ions have nothing to do with acidity, but H ions certainly do. So, what happens is by adding this to water, I increase the concentration of these in the water solution. And therefore, I might go, let's just say I add enough. So what happens is I go from having a concentration of 10 to the negative seventh moles per liter of hydrogen ions to 10 to the negative second. Now that's significantly higher in concentration. In fact, that's what, 10,000 times? 100,000. It's 100,000 times more concentrated. So the pH goes from 7 to 2 because the negative log of this is 7 and the negative log of this is 2. So in other words, before I added the acid, pure water had this concentration of moles per liter, which is this, which is this. After I added the acid, the concentration became much higher. So now it's 0.01 instead of 0.00000001. That's 10 to the negative 2 moles per liter. So that would be a pH of 2. So the takeaway here is, as acidity increases, pH decreases because you have a higher concentration of hydrogen ions. And if we look at a pH scale, just as a reference point, absolutely pure water has a pH of 7. That means there are 10 to the negative seventh moles per liter of hydrogen ions and 10 to the negative seventh moles per liter of hydroxide ions. Now, we're just not going to worry about the hydroxide part of that. All right, but what happens is, as I increase the acidity, as I add hydrogen ions to it, the pH gets lower and lower and lower and lower. So, like lemon juice has a pH of 2, stomach acid has a pH of 1, and then acids we might use in a chemical laboratory can be lower than that. Now, it's worth noting that even when we talk about pure water, that's really something that humans make. Water in nature is not pure water in that sense. So we find is even the quote purest of rainwater is going to have an acidity that is a hydrogen ion concentration that's greater than what you find in pure water. So in other words, the pH is lower than 7. And here's why. Carbon dioxide is a compound that is present in the atmosphere. And carbon dioxide reacts with water. So when carbon dioxide interacts with water, it forms carbonic acid, H2CO3. And this dissociates, forming hydrogen ions and carbonate ions. And I haven't balanced this. It actually produced 2 of these and 1 of these. Now, That means carbonic acid is going to increase the concentration of hydrogen ions and therefore decrease the pH. So instead of having a pH of 7, rainwater has a pH of about 5.6. So it's slightly acidic. And that's because of carbon dioxide interacting with water to form carbonic acid. Well, acid rain means rain in which the acidity is lower than 5.6, implying a higher hydrogen ion concentration. So the main culprit for this is SO2. NO2 does it as well, but SO2 is pretty much the main culprit, okay? And sulfur is found in coal. And so what happens is because we burn a lot of coal to make electricity, what happens is the SO2 that comes out of the smokestack will interact with water, usually in the atmosphere, forming sulfuric acid. Sulfuric acid dissociates to make sulfate ions and hydrogen ions. So it's going to cause the concentration of hydrogen to go up and the pH to go down. NO2, which is released by all forms of combustion, including cars, uh, it also causes an acidity problem because the NO2 in particular reacts with H2O, forming nitric acid. And nitric acid dissociates, making H ions. And so when we put SO2 and NO2 into the air, lo and behold, the pH of the rainwater, the pH of the rainwater goes down, and it can get as low as 4. And that may not seem like a lot. It's certainly, we should note, pH of 4, that's less than vinegar. That's less than lemon juice. It's not exactly going to hurt you. You're not going to, your eyes aren't going to burn. You're not going to get blisters. You're not going to melt. Okay. But the acidity it is more acidic. It has a lower pH than regular rainwater, so we refer to this as acid rain. Now, technically, a better term is acid deposition because it doesn't have to be rain. It could be snow. It could be other things. Now, we'll get to that in a second. So pure, clean rainwater is going to have a pH of about 5.6 because of the carbonic acid from CO2. But when I put sulfur dioxide and nitrogen dioxide into the atmosphere, it reacts to the rainwater, and the pH goes from being here to getting down around here. And that, it turns out, has a big effect on the environment and on other aspects of human culture. So let's just briefly touch on this concept of deposition being the term instead of rain. Okay, so acid deposition is just a general term we mean for the decrease in pH as a result of rainwater or just as of atmospheric uh, moisture as a result of interactions with SO2 and NO2 in the environment. So wet deposition would basically mean I have rain, snow, fog, hail, some sort of atmospheric water, whether it be liquid in the case of rain or fog, or solid as in the case of snow and hail. But it has a higher hydrogen ion concentration, so it has a lower pH. Right? We call that wet deposition. Basically, it's the compounds, the SO2 and NO2 have already interacted, forming nitric acid and sulfuric acid in the water that's coming to the ground, that is being deposited on the ground. Dry deposition means these particles themselves are being deposited on the ground. And if you have SO2 or NO2 on the ground and then rain lands on it, it turns into sulfuric acid and nitric acid. So we refer to this as dry deposition. So it is a pretty good graphic to show this. So man-made sources, we're showing factors, but don't forget cars often contribute quite a bit of this as well. But we find mostly it seems to factories generate the most. So what happens is we put SO2 and NOx in the atmosphere. And we also, it's worth noting there are natural sources of both of these compounds, namely volcanic activity. And so what happens is it mixes in the atmosphere with water. If it mixes with water, we get acid precipitation, wet deposition. That would be rain, snow, hail, or fog. And then dry deposition is just I get particulate matter in the atmosphere comes down and lands on the ground without first mixing with water to form the acid solutions. Now, if we look at a map of acid deposition, be it wet or dry deposition, we're going to find that usually there is a pattern, and that pattern will indicate how the sources that release it um, uh, interact with prevailing winds. So if I have, and so we get the deposition tends to happen downwind of the pollution sites. So if we have a lot of uh, it, coal-fired power plants in this part of the United States in order to make um, steel. Okay, so they're burning a lot of coal here. And what we found is we burn all that coal, the prevailing winds, remember the westerly winds in the Ferrol cell carry atmospheric winds in this direction. And then we get both wet and dry deposition. So you can have places here, like in say Vermont, where it's a very clean state in terms of it doesn't make a lot of pollution, but that doesn't mean it doesn't have a problem with acid deposition because it's being carried to it from other sources downwind or rather upwind. Now, what are the effects of acid rain? Okay, so uh, let's just start with this. One of the main things we see is it affects human constructions, and some of these constructions are things that we really care about. So basically, the main thing that acid dissolves, the two things that dissolves that humans care about in terms of our buildings, is carbonate uh, construction materials, marble, limestone, cement. These all have calcium carbonate. Calcium carbonate reacts quite strongly with acids. It also interacts with metals. We build a lot of things out of metals, so that matters. But just take a look at this picture. So here we have, we have cultural treasures. Uh, Humans have made artwork for thousands of years, and one of the stones that they like to use because it's so soft and easy to shape is limestone or marble, which unfortunately reacts with rainwater. So what we find is that although these things slowly did erode over time as a consequence of normal acidity and rain, with the Industrial Revolution, suddenly we noticed that we were really losing a lot of these cultural um, objects. I don't know if you saw it recently in the news. There was an article about how somewhere, I think it was in Italy, they tried to reconstruct it. And they made this awful, awful cartoonish looking face here, and people are very upset about it. But the point is that these treasures are being dissolved, because of their interactions with acid rain. And now the thing is, there's steps that have been made. So. If you ever have a chance to go to Greece, you'll probably go to Athens. My wife and I were there a few years ago. We went to the Acropolis. I never really paid much attention to the details of the Acropolis. I just knew it was a culturally significant location I should go see. And we got there early in the morning. We were one of the few people there. And I came across this building here, and it just amazed me. They call these the caryatids. They're these pillars that are made to look like women. So beautiful. I took so many pictures, and then I read, oh yeah, these actually aren't the real ones. We had to move the real ones into the museum down the street because they were being destroyed by acid rain, and we've replaced them with replicas. So what you see when you go there are replicas because in order to protect these, over 2,000-year-old treasures, they had to move them out of the rain because it was going to destroy them. So you can preserve things this way, right? The answer is right now, just we're not doing a very good job of getting rid of acid rain. So what we do is we just move things in, but you can't always do that. So there are other cultural treasures that are just too big to move, and people like to carve out of limestone because it's easier to shape than granite. Granite, by the way, does not interact with acid, so. Things that are made out of granite don't dissolve, but things made out of limestone and a lot of sandstones are cemented together with calcium carbonate. So this Buddha here is, I believe it's in China, and it's carved out of sandstone, but that sandstone is bound together by calcium carbonate, which interacts with acid rain. Now, in addition to cultural treasures, there's just infrastructure in our cities, like bridges in particular. They're made out of metals, and metals, if you recall from chemistry, react strongly with acids. So acid rain has a tendency to cause metal fatigue. It corrodes the structures that we drive on and that we build our cities out of, and so it's quite costly to society in that regard. But let's just talk about the environment since this is an environmental science class. All right. Um, One problem in the environment, obviously, is that many freshwater organisms in particular are susceptible to changes in pH. So, what we find is that if the pH of a healthy lake is usually around 6.5, why? Even if rainwater is 5.6, why would it be 6.5? We'll talk about that in a minute. But what happens is as the pH of that aquatic environment drops down to the fives, in the lower fives, we find a lot of organisms die. And if it gets down as low as 4, everything in the lake is going to die. So you end up with these dead lakes where the pH just got too low for anything to live in. Their biologic processes just don't operate at that low of pH. And so lake acidification and stream acidification is definitely a major environmental problem, especially in places that are downwind of these major industrial areas. But let's talk about why it is that the water in our lakes and streams is less acidic than the water coming out of the sky. And it has to do with the buffering ability of the soil and rock material that the water interacts with when it infiltrates. So rainwater coming down. Now, remember, even under ideal conditions, is going to be about 5.6, and under worse case scenarios with all the sulfur dioxide, my acid rain might be as low as say 4. Worst case scenario. Now that hits the ground, and as it infiltrates, well, what's going to happen is it's going to react with minerals in the soil, especially if we have limestone minerals. So if we have calcium carbonate, that really does a great job of interacting with this acid. So by the time that the water uh, uh, leaves the groundwater and enters our bodies of surface water, say lakes or streams, we often find that the pH has gone up to about 6. So in a sense, the soil has, at least in the short term, solved our problem by buffering the acid. Well, but there's a couple problems here, and one problem is, well, every time you dissolve limestone, there's less of it there. So over time, what happens is the soil basically runs out of its ability to buffer, and all of a sudden there's a sudden change in the pH of the lake. Uh, Now, some areas are better equipped to neutralize acid rain. So areas that have limestone, like here's Yangshuo, which is very beautiful. If you ever get a chance to go to China, this is a gorgeous place. Um, the limestone areas are best at it. Okay, so and lots of the world has limestone bedrock, but lots of places don't. So where we have limestone is calcium carbonate, or sandstones that have a lot of calcium carbonate in it, you've got a better chance of doing it. But like here in Korea, we don't have that. So if we have acid rain coming into our soils, well, our soils aren't nearly as good at neutralizing acid rain as other places because we don't have these limestone. There's a little bit of a grid, but not much. So as I was saying, what happens is over time, uh, uh, the the uh, the ability of the soil to neutralize the acids is diminished because the particles that were interacting with the acids get used up in chemical reactions. At which point we start putting hydrogen ions in the lake, and the pH starts plummeting suddenly, precipitously. So you have you have an acid rain problem in the area, but the lakes are okay, and then all of a sudden they're not okay, and everything dies. This definitely happens. But another thing that happens more slowly is that the aluminum level in the lakes increases. And this is because a lot of bedrock that's more granitic in nature, or what we call gneiss, like what we have here in Korea, has a lot of aluminum silicate compounds. These are basically like, well, anyway, mica and biotite stuff, but these aluminum silicate materials. And when they do interact with acids and they release aluminum ions, it turns out aluminum ions are quite unhealthy for most living organisms, be those uh, fish species or plant species. And here's how that happens. It gets into the ground and starts dissolving these aluminosilicate atoms. And so aluminum gets leached into the groundwater and makes its way into our soils and into um, our groundwater and surface water. So another thing to point out is that acid deposition, it has a tendency to kill forests as well as lakes. So what happens is uh, the decreased pH on the tops of trees where the rain is coming down and the pH tends to be lowest, it can make it almost impossible for new leaves to form. So we get what we call crown dieback. The top of the trees become just dead sticks, that they're not growing. They're no longer growing fresh leaves. Usually trees grow from here and they stop growing from here. So we call this necrosis of leaf tissue, just the dying of leaf tissue. And that includes to needle trees as well. But another thing that happens is that when this gets into the soil, it can kill the nitrogen fixing bacteria in the soil. So now the soils are no longer absorbing nitrogen from the air. And so we're breaking that nitrogen cycle. And so now we're not building up nutrients in the soil. So without those nitrogen nutrients, you can't grow these new leaves anyway. And so what we find is as we leach the nutrients out of the soil and kill off the top of these, eventually you reach a place where you get these just forest die-offs. And there are places in the northern hemisphere in particular, we see large swaths of forest that have been killed by this exposure to acid deposition. And then, as I said, with lakes, we get the same thing. When the lakes acidify, when the soil runs out of its ability to buffer, then we end up with sudden lake die-offs. So how do we fix the problem? Well, the good news is a lot has been done. So in my lifetime, we've reduced this quite a bit, even though we've actually increased the amount of coal that we burn. So basically, here's what we can do: we could burn less fossil fuel. After Christmas, we'll talk about how we're going to manage to do that. But for right now, to say that is a goal that we're failing at, but we know that is the answer ultimately. One thing we could do is use LPG, liquid petroleum gas, instead of gasoline. The reason is LPG just burns more efficiently and produces less NOx. So that's one thing we could do. Another thing is we burn higher quality, low sulfur coal. So one of the problems we find is that in a lot of countries, they're choosing to burn the brown coal, the lower grade coal, and it tends to have a higher sulfur content. Now, there's a technology that exists, all right, that will allow us to sort of wash out the sulfur, a lot of the sulfur from the coal before it's used, but that adds to the cost of the coal. And then another thing is, and this is then we'll talk about this, we can employ scrubbing technology. So it is possible to capture a lot of the NOx and SO2 before it leaves the smokestack of power plants. Or, as we said, if we put catalytic converters in cars, that helps. The other thing is we switch to electric vehicles. But still, the problem is we still get, that they still have to be powered by electrical power generation, and that usually means burning coal. So that at this point, until we find some other way of generating electricity, the only reason it helps us with the problem is that we can shift that uh, combustion to point sources in the smokestacks of factories where we might have a better ability to mitigate using this scrubbing technology. All right, that does it for acid rain. Sorry, this was a long one, but thanks for watching.